Friday Technology Talk. In the progress of instrumentation and measurements, one of kind of a foundational transition in how we can look at signals was the creation of the analog to digital converter for computers. So you take an analog signal and you have a chip that can assess that analog signal from 0 to 10 volts. Let's use just a 10 volt scale for my mind. So if the voltage was 5 volts, you could say it was 5 volts. Before, if you had a digital input, you would only be able to say with the digital input that you had a voltage, yes or no. But with an analog converter, analog to digital converter, you can put that into a number. So the two elements to that, and it's usually a single chip with some huge support electronics for stability, for noise purposes. So the two things that changed on that A to D converter, remember, this is over decades. This didn't happen because somebody invented it. It happened because it's been engineered and re-engineered and looked at again. But this is probably this is the key to most of the measurements that we do. It allows us to turn things into CGI that we can visualize and see and make comparisons. It's data versus a meter moving up and down on a panel. So this A to D technology that came in has gone through two major improvements. The number of bits. So it used to be you had an 8-bit analog to digital converter. Let's make it simpler. Let's make it a 4-bit. A 4-bit can count from 0 to 16. Binary math. So with 16 bits, that A to D converter can convert a 0 to 10 volt into 16 values, where the number 16 is 10 volts and the number 0 is 0 volts. So on that A to D, an 8 is going to be 5 volts. From that count, I can create a conversion factor, right? A dose of voltage with that A to D. So the next step there were steps before that, but we started with an 8-bit analog to digital converter that gave us 16 bits of resolution. Or, yes, 16 integers, 16 values of resolution that we can equate to a voltage, because the number 16 in digital equals 10 in the voltage measurement. So now we have 24-bit, and you're going to have to do your own math on that, but how many numbers, how much resolution, if I'm still measuring 0 to 10 volts, how much resolution do I have with a 16-bit A to D, a 24-bit A to D converter? So those incremental tiny little steps in the background that nobody's noticed because their multimeter got cheaper. These VSLI chips got cheaper. These intelligent chips got a lot cheaper. And the people making them got replaced by robots and software. So this is that subtle little analog to digital converter conversation, I suppose, that you can have out there. And I used a scale of 0 to 10 volts. When I put that little 24-bit A to D converter on a Wheatstone bridge, and my voltage range is 0 to 1 millivolt. And I've now got a 24-bit A to D processing 0 to 1 millivolt. And this is complicated translations in your mind. And if I do the math, I slow way down and get confused, but I understand the importance of that resolution, because that amount of resolution is how we are measuring most everything today. We have simply gotten much better, much more precise in what we measure. It's not magic. There's no magic out there. There's no supernatural in these measurements. If we find supernatural, like subatomic particle theory, then we begin to learn about it and understand and refine and define how it interacts with other things around it, right? It's that lone wolf out there in the crowd. It's that level of study. So that A to D converter, the second element was, so we've gotten to a high resolution of a voltage scale, very high resolution of a voltage scale. It's made measurements so much more precise and accurate. It has forced us to engineer better power supplies and better filters and better understanding of particles and interactions. So that is one of the huge pieces, little tiny chip of hardware. Now you put a layer of software on top of that, how to analyze those bits coming into the processor. And that grew. That got exponentially better. It went from paradox spreadsheet and memory resident databases to long historical data sets. Simple A to D converter. A/D converter, look it up and get confused and realize that's the backbone of the measurement industry, especially real-time systems. The faster you can sample that, you've just changed resolution again, because instead of sampling one sample every second, you're sampling one sample every millisecond. These old analyzers that I worked on went from cycle times of minutes to cycle times of less than a minute, just for an example. They went from capillary columns to, well, they went to capillary columns, from diatomaceous earth-packed columns. So surface, boundary layer, physics feeding into a Wheatstone bridge. It's the world we live in. Anyway, enjoy. Peace out. Touch physics in there. Great day.